Hello, dear participants of the symposium on fatigue crack growth and orientation criteria. My name is Mikel Escalero, and I will present a study entitled Trends in Crack Shapes and Crack Drying Force Distributions for Naturally Growing Fatigue Cracks. This work has been conducted jointly by Kerlan Technology Center and the University of Oviedo. The exposition will be divided in 4 main sections. In section 1, I introduce the general motivation and the work's objective after reviewing the current state of the art. In section 2, I present some numerical fatigue crack growth simulations based on our novel methodology. In section 3, I show some theoretical studies to discuss the previous numerical results. And finally, in section 4, I draw some conclusions and define future lines of work. So let's start with the motivation. Fatigue crack growth not only depends on the external oscillating loads, but also on plasticity-induced crack closure, which is the wedging effect produced by the crack face contact during part of the load cycle. The thing is that in general scenarios, the effects of both phenomena vary along the crack front. So consequently, the crack drying force displays through the thickness variations and the crack shape changes. This means that fatigue crack growth should be predicted by pointwise calculations, being for that the finite element method the most popular approach. Reviewing the literature, we see that there are different strategies. Some of these strategies are based on remeshing, and they either neglect plasticity-induced crack closure or they estimate peak by closed form expressions. These strategies are based on a 3-dimensional linear elastic finite element model of the cracked body for sieve calculation, and the crack is grown according to a multiple degree of freedom scheme following Paris-like laws. Through these strategies, it has been reported that there are two stages: an initial transitory stage where the crack shape changes given the initial non-uniform sieve distribution, and a second stage where the crack tends towards a converged crack shape yielded by an iso-K distribution. Additionally, it is known that the final curvature is expected to be greater if peak is considered due to the greater effect of peak close to the surface. There are other strategies based on node release. Here the crack shape can be either fixed or the mesh can be arranged in such a way that by releasing nodes, the crack evolves in a predefined fashion. These strategies are based on a 3-dimensional elastic plastic finite element model of the cracked body with a rigid surface on the fracture plane to simulate peak while we applied load cycles. The trends reported depend on the assumptions on crack shape. For example, for a growing straight crack, the crack drying force profile is kept almost constant as the crack grows, with higher values at the interior than at the surface. For evolving predefined shapes, delta K effective is claimed to tend to iso distributions, although some fluctuations are still observed at the end. Finally, there are strategies that combine node release and remeshing. These are based on 2 3-dimensional finite element models of the cracked body, one linear elastic to calculate sieves and the other elastic plastic to compute crack opening loads. And in order to maintain the load history, information must be transferred. For instance, by starting from scratch with the calculated curved shape, like guarding, or by mapping operations, like gaussing. According to this strategy, the predicted crack shapes have been observed to correlate well with experimental benchmarks, and it has been discovered that an almost constant through the thickness distribution of delta K effective is reached, what according to Gardin permits to ratify delta K effective as the true crack drying force. So, to sum up, we see that most of the present finite element techniques to simulate fatigue crack growth still rely on restrictive hypotheses, what questions the reported trends. Therefore, the objective of this work is to revisit the trends in crack shapes and crack drying force distributions for naturally growing fatigue cracks. For the time being, we delimit this study to through cracks under mode 1 loads. So let's address our fatigue crack growth simulations. In this work, we simulate fatigue crack growth with a methodology recently proposed by the authors. This methodology considers the interaction between plasticity-induced crack closure and crack shape evolution through remeshing and mapping. And the main novelty has been the use of crack tip opening displacement-based fracture parameters. These are elastic plastic fracture parameters, valid both in small and large scale yielding, that intrinsically account for plasticity-induced crack closure. So these fracture parameters, based on CTOD, have the advantage of needing a single finite element model to perform fatigue crack growth simulations. I will explain the methodology by using the example analyzed here, which is a compact tension specimen made of S275 steel subjected to a maximum K of 12 megapascal square root millimeter and a stress ratio of 0.1. So in step 1, the cracked body is modeled by the appropriate Chavosh hysteretic properties and an adequate mesh, which contains a highly refined local region close to the crack front and which also has the contact surface to simulate peak. In step 2, the fatigue process is simulated by applying a load cycle so that the material response stabilizes. In step 3, the fracture parameter acting as the crack drying force is calculated, which in this case is the plastic component of the crack tip opening displacement range that is derived from the nodes behind the crack front. In step 4, the new crack front locations are determined by using the local crack advances computed by the multiple point approach, and the normal directions of the present crack are also used. In step 5, the stop criterion is evaluated to check that the current crack is still acceptable. In steps 6 and 7, the local mesh surrounding the crack front is replaced by the new mesh, and information about stresses, plastic strains, and so on is transferred from the old mesh to the new mesh. And finally, in step 8, the nodes are released to simulate crack advance. And at this stage, the model is ready to begin a new crack advance loop. So, focusing on the local region around the crack front and considering von Mises stresses and equivalent plastic strains, we see that using the proposed methodology, we are able to evolve the shape of the crack thanks to the remeshing, while keeping the load history thanks to the mapping. And all this allows generating the plastic wake behind the shape-changing crack front, as shown in the videos. So let's address the results obtained for the crack in the S275 compact tension specimen. Starting with the crack drying force distribution, we see that for the initial straight crack, delta CTOD plastic normalized by the midplane value is higher at the central region than at the surface, as expected from the literature. Initially, the relative delta CTOD plastic decreases close to the surface as the crack advances, and this is attributed to the peak building up, especially in that region. But then that relative delta CTOD plastic increases at the surface, while being maintained relatively constant in the central region, what leads to a valley close to the surface. So finally, delta CTOD plastic tends to a non-iso crack drying force distribution, what clearly contradicts all the literature available. Turning to crack shapes, we see that in the figure on the left, the evolution of the predicted beach marks, and in the figure on the right, the evolution of the tunneling distance. So initially, the crack shape changes considerably, but then, after a while, the shape change rate decreases and the crack front tends to a converged shape. That happens for this particular case at approximately 1.5 millimeters, what corresponds to 8 times the maximum size of the initial plastic zone. And All these trends are completely coherent with the extensive literature, and moreover, the results are validated, at least in crack shapes, thanks to the high correlation with experimentally measured benchmarks in terms of tunneling at the stable shape regime. Since some of the previous results were contradictory with the vast literature, we performed theoretical studies based on generic fracture parameters, and that's what I'm going to explain now. So the analytical approach consists of considering different ideal crack shapes and consists of implementing the multiple degree of freedom scheme where the crack is grown according to a crack growth law that follows Paris power law. This law is interesting because it encompasses many different fracture parameters that have been historically used as crack driving force. So using the highlighted formulas, we can relate the relative crack advances of 2 points with the values of the crack driving forces for those points and vice versa. So we do 2 theoretical exercises. In the first, we simulate fatigue crack growth under an iso crack driving force distribution by postulating different initial crack shapes, and in the second, we back calculate the crack driving force distribution required to achieve a constant crack shape growth. So let's analyze the results. The first thing to notice is that constant crack shape growth is incompatible with isocrack driving force growth. Why? Because in the constant crack shape growth, all the points advance the same distance in the main propagation direction, whereas under isocrack driving force, all the points advance the same distance, but in the normal directions of the crack front. So these two cannot happen at the same time unless the crack front is straight, what does not happen for naturally growing fatigue cracks. This statement supports the results obtained with our methodology, but contradicts the literature. Moreover, if we postulate an isocrack driving force growth for different cracks with either parabolic, elliptical, or arbitrary shapes, we see that the crack front progressively flattens as the crack propagates, what is inconsistent with available experimental data. Note that the flattening is independent of the fracture parameter and its relationship with the crack growth rate given by exponent C2 or exponent n. Finally, by doing the back characterization of the crack driving force distribution for a fixed shape and assuming the aforementioned parabolic, elliptical, or arbitrary cracks, we see that in fact the crack driving force has to fulfill a non-iso profile, and such profile is found to depend on the present crack shape and the exponent n. So let's finish with conclusions and future lines. In this work, fatigue crack growth has been simulated by a novel methodology to identify the trends in crack driving force distribution and crack shape. This methodology resorts to crack tip opening displacements and accounts for the interaction between peak and crack shape evolution by means of remeshing and mapping. It has been found that there is an initial stage where the crack driving force distribution and the crack shape change considerably, and that's completely in agreement with literature. But the results indicate that there is a second stage where the crack driving force distribution converges to a non-iso profile that produces a shape change that decreases progressively by eventually leading to a stable crack shape. This is in complete contradiction with the extensive literature. The crack shape results are validated so thanks to the high numerical experimental correlation obtained for the tunneling of the stable crack. And additionally, a theoretical study performed based on Paris law relationship and ideal crack shapes shows that in fact, as indicated by the numerical results and contrary to the extended belief, the constant crack shape growth and the crack growth under iso crack driving force distribution are incompatible unless the crack front is straight. Moreover, An isocrack driving force distribution does not make physical sense because such distribution would lead to a flattening of the crack front that is not expected based on experience. And finally, a constant crack shape growth requires, as already mentioned, a non-isocrack driving force distribution, and such distribution depends or is found to depend on both the present shape of the crack and the exponent n that relates the fracture parameter with the crack growth rate. So the remaining work on the view of the potential of the methodology is to repeat the fatigue crack growth simulations with the total crack tip opening displacement range and see if we ratify the discovered trends.